photochemical or photocatalytic process.
So thank you, Frederic, for this introduction. And I'd like to thank the organizers for giving me this opportunity to present this work here. So as Frederic presented, I'm going to discuss the UV-enhanced uptake of SO2 on Icelandic volcanic dust. So we're talking of natural samples. And is it photochemistry or photocatalysis that we observe? A brief outline of my talk. I'll begin with an introduction, then I'll present the experimental method, then I'll move to results and discussion, and I'll end with conclusions. So first, volcanic ash is emitted together with gases during explosive eruptions. For example, this satellite picture of the Eyjafjallajökull eruption in Iceland back in 2010, where you can see here the volcanic ash plume. Ash emissions account for tens to hundreds of millions of tons per year of dust, which represents 1 to 10% of the total primary aerosol emissions. But in specific years, you can have a dramatic increase of these ash emissions from 10 to 10 to 10 to the 11 tons a year, which would then make 40 to 90% of aerosol emissions. And then ash can settle on the ground and be later remobilized by winds. This is what you can see here on the picture. And it is then called dust. So this is what we're going to study in this talk. Now, the volcanic gas in the atmosphere. Volcanoes emit mostly water, and then CO2, carbon dioxide, and third comes sulfur dioxide, SO2. Then you can see minor amounts and trace amounts of different compounds. So SO2 is interesting as in urban areas as a marker of early episodes of pollution, but in this context, it's going to be interesting as a precursor of sulfuric acid and of sulfur-containing aerosols. So it's going to be interesting for the radiative balance of the atmosphere, for example. SO2 concentrations have been measured, for example, during non-eruptive outgassing around Mayasa volcano in Nicaragua. And concentrations up to 90 ppbs were measured with a peak at 230 ppbs within 44 kilometers of the vent. So this is the order of magnitude we're talking of for realistic concentrations. Now, the interaction of SO2 with volcanic dust. We've seen that strong emissions of both SO2 and volcanic ash in the atmosphere occur during volcanic eruptions. Volcanic ash can settle on the ground and is later remobilized by winds as the dust. So this is a picture of Iceland during a dust storm. And this is dust that is this time uplifted in the atmosphere. SO2 can therefore interact with volcanic dust in presence of water in the atmosphere and of UV irradiation during the day. So the question we ask here is, how does V dust modify the atmospheric sulfur dioxide budget? And how does UV light impact this process? The objective of this study is the quantification of SO2 uptake by natural samples of Icelandic V dust. So the importance of having natural samples has been stressed by Daria earlier, and under realistic atmospheric conditions. Second, the impact of UV radiation on the uptake process. And last, we're going to question the nature of UV light's involvement in SO2 uptake by volcanic dust. Now, the experimental method. So first, the samples, they are the ones Daria presented earlier. Basically, they come from Iceland, from different parts of Iceland, and they are dust, so taken from the soil. With different, as you can see on these SEM images, they've got different shapes and different sizes, different porosities, also different compositions. I'll come back to that later. Now, basically, to study this dust in the lab, what we do is to mix them with water, and we deposit them on the inner surface of a Pyrex tube. You can see here that the coating of this Myrdalsandur volcanic dust is relatively homogeneous. And then we insert the tube in a coatable flow tube reactor. So the tube with the volcanic dust is shown here in gray. It's in the reactor, so we've got a double wall with thermostatic fluid. And we have this movable injector to inject basically the compound of interest. That's going to be sulfur dioxide here, mixed with air. And then downstream of this reactor, after interaction with dust, we've got an SO2 analyzer to measure the concentration of SO2. And all around the reactor, we have UV lamps to perform the irradiations. So now I'm presenting a theoretical profile of the SO2 concentration as a function of time during a typical experiment. First of all, we set a stable SO2 concentration in the reactor, and dust is not exposed at this point. We then pull the reactor to expose the dust to SO2. We've got an initial decrease of the concentration we measure downstream, and then after some time, we come back to a steady state. When this is reached, we turn on the UV lamps, and we are going to observe a second uptake of SO2. We go back to a steady state that we measure with the concentration, and after that, we switch off the UV lamps to control the SO2 level in the dark, and then we push back the injector to control the initial SO2 level. From the measurement of the concentrations and the different parameters of the flow and of the reactor, we can calculate the observed constant of the heterogeneous reaction. We correct it for SO2 diffusion, and once we've got this kinetic constant, we can calculate the steady state uptake coefficient of SO2 reacting with volcanic dust. We also have access to the number of SO2 molecules taken up by dust in the dark and under UV radiation, that's the dashed area here. Now I can move to the results and the discussion. So these are experimental traces I'm showing here for SO2 concentration as a function of time, uptake by Myrdal-Sandour volcanic dust with an SO2 concentration of 75 ppb at room temperature. The full line shows a relative humidity of 10%, and the dashed line, a relative humidity of 50%. You can see, so in both parts, the number of molecules taken up in the dark first and under UV light. The first striking thing is that the addition of UV light triggers a new transient uptake of SO2 that you can see here. And so what is very interesting, in my opinion, is that this is a transient effect. We've got consumption of molecules, and then we go back to a steady state that we will see later is basically the same as in the dark. Second point, relative humidity seems to have quite a large impact on this number of molecules taken up, especially under UV radiation. So this number of molecules would be here. And you can see when we increase the relative humidity, we've got a dramatic increase of the number of molecules reacting. So I'm going to discuss now these two parameters, UV light flux and relative humidity, beginning with relative humidity. So we've plotted here this number of molecules, of SO2 molecules taken up by surface area of dust as a function of relative humidity. First thing you can see is that in the dark, this number of molecules increases in a Langmuir-like fashion. So and it saturates at about 30% RH, which is more or less the value that corresponds to the formation of water monolayer on volcanic ash. The second point is that under UV radiation, so with a flux that we've characterized, I'll come back to this later, we've got a linear increase of the number of molecules taken up with relative humidity, and the insert shows that so does the amplification factor of NS, so that is NS under UV light, divided by NS in the dark. So this points to two effects, one of gas phase water and another one of the interaction with UV photons irradiating the sample. So I'll move now to the effect of UV radiation. Again, the number of molecules taken up as a function of the photon flux given as the photolysis rate of NO2 in the sample, in the setup, knowing that typical atmospheric values are between 10 to the -3, 10 to the -2. So this is typically the values we have. And we observe a linear increase again of NS and of the amplification factor of NS with the flux, the photon flux, this time at a relative humidity of 30% at least. So this points perhaps to a photocatalytic effect, the activation of the surface by UV photons, but it could be as well photochemistry, which is alteration of SO2 by UV photons. So how could we try to make the difference between both? What we've done is to measure with XPS the composition of the surface of volcanic dust. And what we see here is the amplification factor as a function of titanium concentration, so in the surface of dust. And here, the ratio between titanium to silicium concentrations at the surface of the different samples of volcanic dust. So for this photon flux and relative humidity of 30%, we see that the amplification factor increases linearly with titanium content and also with a ratio of titanium to silicium. So we have a proportionality of the amplification factor with surface titanium content, which could suggest photocatalysis, but at this point, we cannot rule out completely photochemistry. What we can do with this is a global parameterization of the NS amplification factor with the different parameters we've investigated. So this is relative humidity, photon flux, and composition of the surface. So empirically, we obtain a quantitative relationship linking the amplification factor with these parameters that are displayed here. And this equation can be quantitatively interesting for people of the modeling or simulation community to implement chemical schemes of the atmosphere. Now, I'll briefly go to the steady state. And as I explained earlier, we can calculate the steady state uptake coefficients of SO2 on the dust. First, I plot here the kinetic constant as a function of dust mass. So we have a linear increase of SO2 uptake with V dust mass, which means that all the dust is exposed to SO2 in this regime. And when we go to the BET, a steady state coefficient as a function of relative humidity and both in the dark, in black, and in yellow under UV light, what's interesting is that we see an increase first of SO2 uptake up to 30% RH. Then it plateaus, it decreases and plateaus until 70%. Again, this behavior could be linked to the formation of the water monolayer at an RH of 23%. And what is spectacular here is that steady state uptakes are similar in the dark and under UV light. This is completely different from what we've seen for the number of molecules taken up. And therefore, UV radiation does not seem to produce any detectable quantitative difference on the steady state behavior or on the steady state conditions of SO2 uptake by Myrdal-Soldow wind dust. I go now to conclusions. So we have quantified the uptake of SO2 by natural Icelandic volcanic dust samples under realistic atmospheric conditions. SO2 uptake is efficiently promoted by UV light and relative humidity. And as we've seen, this is a transient promotion of the process. We do not see any difference at steady state. Photoactivation of the surface of Venus is suspected, but at this point, photochemistry cannot be ruled out. So more work is needed to understand this complex but realistic system. So I'll thank my colleagues at IMT Nord-Europe and at University of Iceland, Pavla Dagsson-Waldhauserova for providing the samples, different sources of funding, and last, I've got something very quick, a call for papers that may be of interest. I am a guest editor for Frontier in Astronomy and Space Sciences, together with Manolis and other people. And in the astrochemistry and planetary science sections, we are calling for papers about heterogeneous processes on dust and ice surfaces, which would be relevant for planetary atmospheres such as Mars, Venus, Titans, Earth as well, if it has perspectives for exoplanets. So submission deadlines are quite far from now, but if you're interested, please keep in touch. And I'll stop here because I guess our Belize can't take it any longer. So thank you for your attention.
Thank you, Jerome. We have time for maybe one or two questions, and it's good to see that sometimes it's better not to over-conclude about the nature of processes. So, is there any question in the chat? I don't think so.
Everybody's gone for lunch.
Maybe you're not on the right time. Is there any question in the audience? No question in the audience? Oh, Daria. Daria, you can come here and raise a question to the wall.
I have a question, and maybe some other people are wondering, how can we differentiate between photocatalysis and photochemistry in the further experiments?
Well, the point would be to basically observe first qualitatively what's going on the surface, because with quantitative studies, we're not going to extract mechanisms. So the first thing would be what you've done, for example, studied with drift to see what species we form on the surface, and then try to figure out what the mechanism would be specifically for photocatalysis, specifically for photochemistry. And from the balance in the product yields, perhaps we could climb back to which part of the mechanism is the realistic one, if not a mixture of both photocatalysis and photochemistry.
I would add maybe something. If it's really photocatalytic, I mean, it has to satisfy some very specific criteria to support the fact that it's catalytic. And it would be very interesting to look for the turnover number or turnover frequency of the process. And compared to that, considering that what Jerome points at is that the UV impact is mostly on the transient phenomenon, it means that it stops. I mean, even if it's after a few hours, it means that to some extent it stops. So it suggests that it's not really that catalytic, but maybe rather related to photochemical groups that are maybe sensitive on the surface to photons. So this is not clear to the moment, but it's better not to run into a conclusion that could be maybe questions soon. Okay, thank you, Jerome. Thank you again. So now we are moving for two short communications. There are posters, they were selected as posters, and they give the opportunity for a short talk of 2 minutes. The first one is given by Manolis Romanias again, Understanding the Atmospheric Aging of Mineral Dust During Transport, a laboratory approach with colleagues handling the Sesame facility at LISA in Paris.
Okay, thank you again, Frederic. So I'll try to be short in 3 minutes. So actually, what I was mentioning in the morning talk was that we are really suffering of understanding the aging of dust particles in the atmosphere, especially and it's difficult for us in the lab to simulate that. So what we tried actually, this is actually this atmospheric aging can impact the hygroscopic and optical properties of the particles, and thus their impact on climate and also air quality. So what we have tried actually to do is to simulate a dust storm in the lab. So we've done these experiments in the atmospheric simulation chamber there is in Paris, called the Sesame chamber, is a stainless steel chamber. And what we have done, we have made a dust event, so using high concentrations of particles, of aerosol particles in the chamber. And we've used three different reaction systems to study. So we consider three different scenarios. The first one concerns a dust storm, let's say, hitting a forest area. A dust storm, the second scenario, a dust storm hitting an urban area, where we use as a model pollutant toluene an OH radicals reaction. And the scenario 3 was the nighttime degradation of an important compound, biogenic compounds, biogenic compound like limonene. So actually consider, let's say, we made these simplified approaches, but it should not be viewed like this. Each reaction system that we studied actually contains around 2,000 to 3,000 reactions. The challenging step in this campaign actually was to avoid any nucleation formation. So the organics that we used and the radicals, normally they produce new particles. So the challenge was not to produce new particles, but to cover, to coat the dust particles. And we managed to do that with the presence of the seed of the dust. We can discuss later on if you want. So we use a bunch of different instrumentation to control both the gas phase and the particle phase and monitor actually the difference in the hygroscopic and optical properties of the particles and also the chemical evolution of the coating. And here you can see a part of the results concerning the scenario 3, which is actually the oxidation, the nighttime oxidation of limonene. And I just want to briefly say that as soon as we introduce the oxidation, so first we introduce the dust particles and then we start the oxidation of the organic to form the coating. And what we see actually is the increase in the optical, the modification of the optical properties of the particles, as you see here in a blue color. And also we can see a small increase in the hygroscopic properties, which actually they're completely modified when we irradiate our gas mixture, gas and particle mixture in the chamber. So the major conclusion from this was actually that we managed actually to simulate the dust storm in the lab, and that these kind of processes are really important to understand the aging of dust particles in the atmosphere. Thank you.
Okay, so I think Manolis is ready for any interaction in case there are some questions about this short talk. And the next short talk is has been recorded earlier by Antonia Zogka. She's currently postdoctoral researcher at IMT Europe, and she's going to come back on the interaction of glyoxal with gobi dust.
Hello everyone, my name is Antonia Zogka. I am a postdoc at the Institut Mies Telecom in Douai, in France, and I'm going to present you a heterogeneous interaction of glyoxal, an end product and key atmospheric species with gobi desert dust. The objective of my study is to investigate the reactivity of glyoxal, adsorption-desorption, on natural gobi dust under atmospheric relevant conditions such as pressure, temperature, and relative humidity. To be more precise, we measure the uptake coefficient gamma, the prime values, the value for 1 day, and the steady state gamma. In addition, we measure the glyoxal total uptake capacity, NS, and the percentage of glyoxal that stays adsorbed. For all this, we investigate the dependency on the concentration of glyoxal, on temperature, on relative humidity, as well as the light effect. The experimental setup consists of a flow tube reactor where we deposit the gobi dust, as you can see here, coupled with a selective ion flow tube mass spectrometer, and glyoxal is detected at its parent peak with a very low detection limit. So, how does a typical adsorption experiment look like? We introduce the glyoxal and then we exposure the surface. So, we observe the adsorption. From this kind of experiment, we measure the gamma prime, the gamma for 1 day, and the gamma steady state. The uptake coefficients have been normalized using the bed-specific surface area in order to get the bed uptake coefficient. Here in this graph, we have a gamma bed time evolution for a typical experiment. As you can see, the uptake coefficient decreases with time. So, finally, the gamma for one day is 10 times less than the gamma prime. Here, in this graph, we can see the uptake coefficient gamma prime as a function of glyoxal concentration. Points in red and blue represent dry and 30% relative humidity, and we can see that gamma prime decreases as the concentration is increasing. In addition, we observe that there is no relative humidity dependency below 30% of relative humidity, while above this threshold, the gamma prime decreases. The red line here is the fitting of the experimental data using this power function. The concept of gamma prime is based on the scenario where a dust storm meets a glyoxal plume in the open atmosphere. Therefore, gamma prime is very useful for modelers, and the expression that we provide can extrapolate the uptake coefficient under various concentrations. Thank you for your attention.
Yes, we can thank Antonia for her very dynamic presentation. And now we are reaching the last talk of this session. This talk will be given by Pavla Dagsson-Waldhauserova. She comes from Iceland. She has provided several samples that have been discussed and explored in this session, and she's going to tell us about the impacts of high latitude dust on atmosphere and climate. And it makes some kind of nice transition toward the session of this afternoon, I think, before going for lunch.
So good morning, everybody. It's a great pleasure to be here. So I will exactly make the transition to the afternoon, but also explain better where are the samples coming from, those what the previous presentation being provided. And the results I'm going to show here, it's actually based on a huge cooperation with different research groups in Europe and United States. So just the talk outline would be about the high latitude dust sources and their contribution to the global dust budget, and then updates on the high latitude dust research, nowadays mainly on focus from my working group, so it means from Iceland and Antarctica. Then I would like to show you one event which finally provided evidence that Saharan dust can travel, of course, all the way to the Arctic, but with evidence from Iceland, and the impacts of Icelandic dust on atmosphere and climate, just in few slides at the end. So quickly summarize, there was this important paper back in 2016, which was a first overview on the high latitude dust areas. They are both located in the northern and southern hemisphere. For the northern hemisphere, it's mainly in Alaska, Canada, Greenland, and Iceland. And for the southern hemisphere, it's mainly from dust from Antarctica, Patagonia, or New Zealand. The first estimate is that the active high latitude dust sources cover over 500,000 square kilometers, and their contribution is about 5% of the global dust budget. So here are some satellite images of 100 kilometers long plumes from Alaska or Patagonia or Greenland. And the newest images now from Svalbard and also from Antarctica, where there is a new winter just starting, but from the past summer, which was extremely dusty. And when we look at just to the Arctic regions, the northern high latitude dust sources and their contribution to the total dust deposition in the Arctic, so it's estimated that there is a 3% of global dust emission coming to the Arctic from high latitude dust sources, but the most important sources provided the dust in Arctic are from Asia, Africa, and about 27% comes from high latitude dust sources. And for example, for the Icelandic dust, which is in the lower row in the middle, you can see that the emissions actually can reach up to 7% can reach the high Arctic, which is 80 degrees north, and 3% is estimated to be deposited in Europe. But there are also other high latitude dust areas which are very highly unknown. For example, here are images from North Eurasia. In the maps, they are depicted with the yellow circles. And based on that, at the moment, we are actually concluding a new paper on high latitude dust areas. It's led by Outi Meinander from the Finnish Meteorological Institute and about 50 co-authors. And we are including additional 40 new high latitude dust sources from where we have evidence of dust plumes or just evidence. And also the group from the National Hydrometeorological Institute in Serbia, they actually are working on creating this Arctic domain high latitude dust source operational model called DREAM. So here is one example of showing emissions from multiple sources in Arctic high latitudes. And another important source for you to look at the sand and dust active sources, it's a new map from Anna Vukovic, was published under the United Nations Convention to Combat Desertification. And this map, of course, also includes the high latitude dust sources, but for you from lower latitudes, I also recommend this to check, for example, quite dangerous sources such as agriculture fields, for example, in Germany and Poland, causing quite dangerous dust events. But for us, as the high latitude dust sources are the most important, we are now providing the map of these sources and their sand and dust storm index, that means the severity of and probability of the dust events, also on the seasonal variability, because it's changing in summer, winter, spring and autumn. And this map will be provided for the newest Arctic Monitoring and Assessment Program report on short-lived climate forces now in 2021. But the most important source of information is from the Ice Dust Association, Icelandic Aerosol and Dust Association, and we have added under the publication the new area of research, and that's on the high latitude dust sources. And just from past 2 years, you can see the number of the papers from different sources is increasing. For example, Antarctica, Alaska, Canada, and Svalbard. So here are the updates on the high latitude dust research nowadays. So at the moment, the Icelandic Aerosol and Dust Association actually includes 46 institutions. Some members are also here with us today from 17 countries, and we have also almost 100 members, and there are over 60 papers published on this topic. And also important cooperation was created under the InDust Cost Action, which is just about to end right now. And the results of these huge cooperations, there are two big points I would like to emphasize. So it's that there is a first high latitude operation dust forecast from the DREAM model, and that's you can find these forecasts under the World Meteorological Organization, Northern Africa, Middle East, Europe, Regional Center for Sand and Dust Storm Warning Advisory and Assessment System. And another big achievement has just happened few weeks ago, that we had the largest, and I wouldn't actually be scared to say also the largest dust field campaign generally, but also largest high latitude dust field campaign, which took part in July to September 2021 in the Northeast Iceland. And there were several research groups, but we were in total 11 institutions from 6 countries, and we employed more than 70 instruments, including 12 meters tall tower, to understand the dust processes and dust suspension in Iceland. And yeah, it was an extremely special place because the desert is located between the stratovolcano of Askja in the northern part here and Vatnajökull glacier, and in between is also the new lava which is covering the major parts of the dust hotspot from Hollow-Rain in 2014 and 15. But still, it was very extreme. And here are some images from the days when the weather was really nice. And here, just to let you know about our Icelandic observational network. So far we use the camera system, the French Enlabs cameras, which can produce images from 220 degrees, and we monitor the most active dust hotspots, which are always close to the glaciers. And that's what I'd like to emphasize here. The areas which are marked here by orange and red are the areas with extreme and severe erosion, cover over 40,000 square kilometers, which in terms makes Iceland the largest European desert and also one of the largest Arctic deserts. But the deserts itself are not created that you would have volcanic eruption which produce ash and then lately is resuspended. The majority of the materials come on daily basis from under the beneath the glacier, so it's the glacial processes. But of course the mother material is volcanic. So for example, during this huge campaign, we had these horrible floods because there were extreme temperatures in Iceland. And after one flood, when the water has disappeared, our instruments were buried in a layer of 26 centimeters of new fine material. So this is the main source of the suspended dust. Yeah, and from the measurements back in 2020 and 21, it has confirmed that during these storms, we can easily actually reach concentrations of PM10 up to 50,000 micrograms per cubic meter. And this has been again confirmed by the other instruments we have employed this summer. But also dust is from Iceland emitted into higher altitude, as we were sending balloons since 2013, and this has been confirmed that in the higher altitudes, the Icelandic measurements on particle number concentrations were very similar to those measures from the dirty Saharan dust layers. And finally, I can also provide evidence on the long-range transport of Icelandic dust towards Svalbard and Europe, because there are 3 new papers. One is actually older one from Mesa Station in Ireland that has confirmed the volcanic particles presence, which actually gave very similar fingerprint in their measurements as black carbon, because the Icelandic dust is very dark. But then also there is evidence from Svalbard that they have reached our sample, our type of volcanic glass and volcanic dust, and also from Serbia. So indeed, it's confirmed that Icelandic dust can travel over 3,000 kilometers. And as for the research group from Italy, from Svalbard, they have stationed in Svalbard, they also, based on the mineralogy and specific markers, use the potential source contribution function analysis and can distinguish from where is the dust arriving to, from which high latitude dust sources has the dust arrived to Svalbard. So they identify sources in Eurasia, Iceland, Greenland, and Alaska. And using the DREAM model I was showing you, we have just identified actually up to 71 long-range dust event transport just in past year. Here is one example of them. And second part of my research is from Antarctica. So back in 2018, we have actually provided the longest measurements for particle matter larger than 1 micron, so up to 10 microns. And from almost a 3 months campaign in the summer, the mean concentrations for PM10 were about 6.4 micrograms per cubic meter. And this is basically a very similar number to cleared background stations in Northern Europe. So that was in 2018. In 2019, we have small failure, but 19, but now in 2021, the concentration were significantly higher, and these are the preliminary results from this extremely dusty and warm summer in Antarctica, when the daily concentrations actually of PM10 reached up to 40 micrograms, and we know this is an enormous number for such remote areas. And the source is dust. And here is just to show you the presence of Saharan dust in Iceland. So based on the research of the group from University of Birmingham and Clarissa Baldo, she compared the composition of Icelandic dust, several hotspots, and African and Asian dust. So again, the main mineralogy is that we have this volcanic glass. So when you have quartz in Iceland, you are very positive about it, that it's not from Iceland. So we, together with another group from Hungary, Yuri Varga, we published this paper when we look at the long-range transport even of Saharan dust towards Iceland. And based on that, on more than 10 years, 13 years long analysis, we identify 15 Saharan dust events going to Iceland, and 2 of them we actually collected also the samples. And the major findings is not only that there are new pathways like transporting the dust towards north from Sahara, but also these particles are actually giant. So we collected quartz particles up to 100 micrometers. And here the impact, so this is only what I'm going to repeat here on behalf of our colleagues from France. So there is obviously interaction between volcanic dust, atmospheric chemistry. So the dust particles can serve as an uptake of either NO2 or SO2, and we have heard about this before here, so I will not repeat it. But as from the point of climate points of view, there is a new study from the University of Leeds, which actually proves not only on the modeling part, but also aircraft measurements, that Icelandic dust indeed makes ice in the clouds, which in this part of the world is very important. As we know, the Arctic is warming 3 times faster than the rest of the Earth. So main outcome is that Icelandic volcanic dust is an active ice nucleating particle, similar to low latitude dust, but for temperature above -17 degrees Celsius, it's even more active. And the thing, what is happening in the cloud is that the Icelandic dust causes the reduction of supercooled water in the cloud, which in terms changes in the ice, decrease the shortwave reflectivity of the cloud. And that's the main, not very known impact of the particles on these mixed phase clouds. And also the deposition of dust on glaciers. So there has been lately new study on albedo variability in Iceland between 2000 and 2019. And if you remember, there were 2 massive eruptions in 2020, 2010, and those, I mean the explosive, not effusive, in 2010 and 11. And on these little images, you can see the albedo changes every year, but the reddish here, 2010 and 11, shows the massive deposition of dark volcanic ash in terms of several centimeters. But then the year 2019, which is quite reddish, showing also the reduction of albedo. So that was just caused by the dust storms. And on the largest glacier, Vatnajökull, you can clearly see the dust path just from the true color images of satellite. And based on the cooperation with our Finnish colleagues, we have made several experiments on dust deposition, volcanic silt and sand, deposition on clean snow in Lapland during the soot on snow experiments, and we compare the changes in spectral reflectivity of the snow with soot from Helsinki chimneys. And the main result is that the volcanic dust actually decreases the albedo similarly as black carbon, and it affects the water retention capacity and also density of snow. So we have introduced this dust albedo effect. And yes, to the marine environments, and Clarissa Baldo will likely talk about this later during this conference. So there is different iron content and iron solubility in different dust. So for the Icelandic dust, it changes between the hotspots, but for the Dinghu Sandur, where was this large field campaign, the solubility is quite high, up to 0.6%. that also has important impacts on the ocean we shall focus. So, and here are a few last slides of my presentation. So again, instead of concluding the points I've showed here, I would like you to maybe visit our website of the ISDAS Association, where you can see under the tab of publication, different list structure, all papers published on high latitude dust and Icelandic dust. And we meet annually every February. So the next high latitude dust workshop is on 15 to 16 February. Everybody is welcome to Reykjavik. It's free of charge. And also we have the session at the EGU. And yeah, this is just, I wanted to include it in the last experiment. We also had artists with us, which created amazing like performances and nice studies like we scientists do measure with our instruments or in our laboratories, but it's hard to explain it to general public what means what concentration. So the artists can experience the concentration with their own body, having the jars and bring it closer to the people. So that's going to be available on the ISDAS Association website too. And this is my thank you with several images from the campaigns and latest eruption in Reykjanes. Thank you.
Thank you, Pavla, for providing this nice overview of the high latitude dust. Sorry? Yes, I think there was a question online. True. And thank you for ending up on an RT picture. It's good to end up on art after one morning of science.
Yeah.
Okay, so where are the questions? I think you've got two questions online. Zombo. So, Pavla, thanks for the update. How the dust concentration was measured. Sorry, I might have missed what you said. OPC, if so, were they calibrated against reference instruments?
So, the Icelandic-based instruments are the dust track and light aerosol optical counters, which has been also calibrated against TIOMs, which are run by the Environmental Agency of Iceland. But latest campaign where we had, as I mentioned, over 70 instruments. That will provide really one of the most closest calibration possible. So over there we also had FIDAS and VELAS, several cheaper OPCs, dust tracks and LOACs, and based on that we will have high resolution concentration information. So I hope it helps.
Okay, I hope it will help our colleague Zombo. Is there any question in the audience, in the room? I don't think so. Oh, Manolis, you've got a question.
Yeah, I have a question from just you showed that the impact of deposition of volcanic dust, to the Arctic is similar like soot. Does it mean actually that the optical properties of volcanic particles are similar to soot particles?
Yeah. Maybe just to make sure that people online have heard the question. It's a question about optical properties compared between soot and volcanic ash or dust.
Yes, so to my knowledge, I am aware there are now several research groups working on this to be able to answer this. And I guess we can even ask about presenters later also here actually two of them in the dust conference. But based on our measurements with the Finnish, sorry, I have to take it, so hard to read. With the snow experiments, we compare the spectral reflectance with the ACD spectrometers, but also other type of spectrometers. And it showed both on the snow, but also in laboratory that the albedo itself or the reflectance of soot was about 0.0, I don't remember exactly, but the spectral reflectance of Icelandic dust was 0.03, which is nearly black body as well. But it differs from the sources, and of course it depends on size. So yeah, that's a topic to look at.
Thank you for your questions. I think we can end up here this session, dealing with the interaction of many species with the surface of various dusts. I really want to thank again the speakers who have made their nice presentation ready on time, respecting the time. I want to thank those who have made the decision to come And I want to thank those who have decided to be online, to be present and upload their presentation earlier. It was very good. And I also want to thank those who have raised questions to help the debate make it being more vivid. So thank you again and have a good lunch.